All right, what's the smallest machine that can learn? So let's imagine this right here is our machine. And to start off, we're going to give our machine two knobs, sort of like dials. And each of these dials or knobs is going to have a value attached to it. Now, these knobs can either be tuned up and this value will be increased, or tuned down and the value will be decreased. These are called weights, and we can label these as weight number 1 and weight number 2. So now that we have this machine, let's think about what we're going to feed into it. What's our input going to be? The simplest thing would be two states, right? Binary states. Off, we can characterize one of the states as off, and the other states as on. In order to think about all the ways that these two states could be classified, we want to look at all the possible combinations, right? So we could have on, off. We could have off, on. We could have, both on, or we could have both off. But we can't feed in these words into our machine. So we have to encode the two possible states in numbers. Now, the traditional binary encoding would be off as 0 and on encoded as 1. But for the purpose of this video, it would actually be better to do off as -1 and on as +1. That way, our two binary states are sort of revolving around 0. Like 0 is kind of like in the middle between them on the number line. If you imagine a number line, you have 0 in between these two. And that way it's just going to allow us to visualize how our machine is working more geometrically. So let's encode off as -1 and on as +1. And we can draw a table, but now with the numbers. So every possible combination of these numbers. And it's representing the same thing, just numerically, right? So there's 4 possible combinations. And we can label these two inputs as variables because, they might be different each time. So let's label them as input number 1, x being input, and input number 2. All right, so we're going to feed these input pairs. We can call each of these an input pair. We're going to feed these input pairs into our machine. And now we need to think about what is our machine going to output. So we can say that our machine is going to output a score for a given input pair. And that score will have a sign that's either positive, meaning the number that it outputs is positive, or it'll be a negative score. And based on that, the machine will classify our input pair. So it can either say, a given input pair is positive or a given input pair is negative. We can formalize this in a very simple formula, which is basically just our first input multiplied by our first weight plus our second input multiplied by our second weight is equal to the score for that given input. Now we can denote the score as Z, but let's just think about this for a second. So if we want our machine to evaluate a given input pair, we would substitute in x1 an x2 as like a pair. So it might be, I don't know, -1 and 1. It might be 1 and -1, etc. And our tuned weights, whatever they're tuned to, will then scale those inputs. And when that's added together, it's going to give us a score. And based on the sign of that score, that's going to be how we classify that input pair, right? Now we can actually visualize how our machine is making this classification in a way that's going to give us a very nice and elegant geometric intuition. So let's imagine a two-dimensional plane. Now, you could plot any point on a two-dimensional plane, and theoretically it extends forever. But here we're just going to want to look at a sort of bounded two-dimensional plane within the range of the numbers we're evaluating. So the upper range is going to be +1, and the lower range is going to be -1. And we can actually plot all 4 of our input pairs on this plane. So if we interpret the first number in the pair as the x-coordinate and the second number in the pair as the y-coordinate, so sort of like the traditional xy. Now, it's kind of easy to confuse these two x's, but this means input and this is the x-coordinate. They're completely different things. They're just, happen to use the same letter. But like theoretically we could, use whatever we wanted for that variable. Just don't get them mixed up. So we can plot these coordinate pairs on our plane. So let's do that. So this first pair would be -1 on the x-axis and +1 on the y-axis. So plot it right here and label it -1 and 1. And let's do that for all 4 points. So now, as you can see, we've plotted all 4 of our possible input pairs onto this two-dimensional coordinate plane. And this is going to allow us to visualize how our machine is actually going about making these decisions in a way that gives us some really useful geometric intuition. So right now, if our weights are set to 0, no matter what point we throw into the formula, no matter what point we throw into our machine, essentially, it will return a score of 0, right? Like, if we were to throw in -1 and 1, so this point, and get it to try and score that, because our weights are at 0, it would essentially scale them both to 0, and our score would be 0. But let's imagine, for example, each of our weights dialed to 1. Our inputs wouldn't be scaled any bigger or smaller. They would just be multiplied by 1, so they would be preserved. So this is like a good example to look at. With our weights dialed to 1, if we were to plug in this point right here, we would get a score of -2. So the sign would be negative, right? So we can already start classifying these. We could say, this point is classified as negative. This point is classified as 0, so we can kind of leave it sort of unclassified. This point is also classified as 0. Interesting. And this point would be positive, right? Now, I don't know if you're seeing the pattern that's starting to form, but I want you to notice that this is a 2D plane, and we're trying to classify these 4 input pairs, but theoretically we could feed any input pair into our machine, and it would return a score. So, for example, say we were to sample a point that's like -0.4 on the x-coordinate and 0.4 on the y-coordinate. If we were to plug in that input point to our machine, With the current weight configuration we're looking at for this example, the score would also be 0. Now, any point we'd sample on this line right here, you can draw it by connecting all these zeros, would return a score of 0 with this current weight configuration. That's pretty cool. Now, any point we can think of on this side of the line, all the way to infinity, would have a score, would return a score if we were to plug it into our machine. It would return a score whose sign is positive. So it would be classified as one category. And likewise, any point we sample from this side of the line, when plugged in and fed into our machine with this current weight configuration, would output a negative score. And that would give us another class, right? Now this line right here, this line where the score is equal to 0, we can call that line the decision boundary. Because on one side of the line, our machine has made a decision. On the other side of the line, our machine has made a decision. But on the line, it's sort of undecided. The point is neither positive nor negative, right? So we call this the decision boundary. Now, if we were to adjust these weights and tune them, it would actually move the decision boundary. And the way that the decision boundary moves can also be visualized geometrically, and there's actually a geometrical intuition to it. So let's look at that. So in order to understand how our decision boundary moves according to the configuration of our weights, we can actually interpret our weights as a coordinate pair as well. So for this example, this example configuration, our weights 1 and 1 would be, they'd fall on the same point as this input point we were looking to sample. Now that's sort of a coincidence, so don't be too confused by it. But for this example, our weights as a coordinate pair are actually at this point. Now, what's the relationship between this point and the orientation of the decision boundary? In order to understand this, I can draw an arrow from the center of the decision boundary to where this weight coordinate is. Now, mathematically, the decision boundary is always at a right angle to this arrow. Now, what does this tell us? If we were to tune these weights and say, slightly decrease this first weight, which would decrease the y coordinate, that means the arrow would be like this instead, right? And so the decision boundary would rotate to preserve that right angle, because mathematically this arrow, which we can call the weight vector, it's a fancy term for this arrow, needs to preserve that right angle. Now, let's say we wanted to put 3 of these points on one side of the decision boundary and 1 of them on the other side. With this current setup, with our machine looking like this, just having 2 weights, no matter how we arrange the weights and rotate the decision boundary, let's say we have the decision boundary like this, or let's say we have it like this, we're never going to be able to have 3 of these on one side and 1 on the other. It's just not possible. So we need to find a way to somehow shift the decision boundary along this weight vector. Let's draw, a new decision boundary in brown. And let's say we were able to shift it up the weight vector a bit. Then, this whole side would become part of this class. And we could classify more flexibly, right? Now, all that we're missing to be able to do this is one more knob. Just one more knob. But this knob is a little more simple, actually. We can call this the bias knob. We'll denote it B. Now, this knob also holds a value like the others. It also can be tuned up or down, just like the other knobs. The only difference is that it doesn't scale any input. So in the formula, it would just look like adding a constant term to the formula, so plus B. It's not scaling any input. Regardless of the inputs, it's always just going to be added to the final score. That's why we call it the bias knob. Kind of gives our machine a little bit of a bias. And just adding that constant term mathematically is going to allow us to shift this decision boundary, which is going to give us a lot more expressive flexibility for classifying. Now, this is the simplest machine that can learn. And to tune these knobs and have it learn a sort of like desired target, we would use something like a learning algorithm, right? Which we're not going to look at this video. We kind of just been messing around with it manually, but you can imagine an algorithm that's just slowly adjusting the weights until all the targets are met. What's interesting for this video to take away and kind of ponder on until the next video is that we now have the expressive power to sort of classify 3 of these inputs as one class and 1 as a second class. So these 3 could be positive and this one could be negative, or these 3 could be positive and this one could be negative, and whatnot. But now, imagine we wanted, for example, these 2 to be classified as positive and these 2 to be classified as negative. There's no way, there's no possible linear boundary that we can draw to possibly separate these. It just doesn't work. And so that's a fundamental limitation of the simplest machine that can learn, right? It would be too easy if it could do everything with 3 knobs, right? And this was actually a big problem in machine learning for a long time. And it took a number of years to figure out a good way to kind of upgrade this setup to be able to classify this problem, which is called formally the XOR logical operator. You don't have to worry too much about those fancy terms, but it's just a kind of way of characterizing this problem. In the next video, we're going to look at the solution